I guess we should start now. So I'll just introduce myself. My name is Himanshu. I'm a fourth year PhD. I majorly work on interpretable and secure or safe NLP. Right. So I'll just start on the session. So instruction tuning on Llama. So Professor Pavan has explained about like how we can use Plan T5 and like all other models, and how does exactly this fine tuning instruction fine tuning works. Right. So majorly, I'll just start with. So earlier we have seen like there are a couple of models which are, let's say, not so smaller models, but still considered as large. So let's say 8 billion parameters, and these models are very good at doing certain tasks. So let's say language understanding, arithmetic operations, or let's say question answering. Then there comes up like say certain like mid-level kind of LLMs, so which are like certainly good at other tasks as well. Let's say summarization, translation. Then you have code completion, and then common sense reasoning. Right, but if you so as we increase the number of parameters, so we will also see. So these models are very good at doing like certain other tasks also. So let's say logical inferencing. So where you are supposed to give some logics, right? Like, or let's say semantic parsing, or let's say general knowledge, or let's say physics Q&A, or let's say joke explanations, translation. Like there are certain other tasks which these models are really good at, right? So what exactly do this kind of, let's say, very large models, like how are these models very different from the smaller models? Like what exactly is missing? So like recent works have shown like these models are very good at giving reasonings, are able to understand the text and the semantics like very nicely. So I'll explain like how exactly these models are able to achieve those abilities. So one of the reason is instruction tuning. So instruction tuning is nothing, it just involves the fine tuning the model on certain instructions. And instructions, so Professor Pavan has already explained like, how instructions look like. So in this hands-on, like I'll just explain how we are able to use these instructions and how we can fine-tune using these instructions. So again, so the important steps in instruction fine-tuning is your the major like your focus and your effort is involved in dataset creation, and then the standard fine-tuning process. So people focus, or like people use this standard kind of pipeline. So where they where they put their major effort on the dataset creation, then the standard fine-tuning will also help. And then at the last we have evaluation, and then okay, sorry. So and then you have the iterative improvements you can do similar to RLHF we do. So these are certain processes. So data set creation. So I will initially I'll first of all I'll start with the data set creation. So I'll be using certain libraries. So I guess majority of us knows about the transformers, and also then we have other libraries which we'll be using. So Llama 2 model, so 7 billion model we can't fit on Colab, so we'll be using uh, quantized version of LoRa. So we'll be using the LoRa methods. So then you have, let's say, bits and bytes. So again, this is a very popular library which is used for quantizing any large language models, and where you are able to, let's say, memory footprint is also very low. And then basically you can fit given your GPU constraints. Then you have PEFT. So PEFT is another, let's say you are in this LoRa technique. So you have this adapters. So PEFT is basically like parameter efficient fine tuning, where you only fine tune a certain, let's say, adapter. So adapter are nothing. So given, let's say you have a transformer model, and then you have your MLP. So you put your feed forwards and you inject those weights of your feed forward of your adapters into your main feed forward of your transformer. So this is how this PEFT or this adapters work. Then you have TRL. So TRL is a library that has this supervised fine tuning. So there's a class, there's a function which has this SFT. So I'll explain in the later part. So how you'd use this SFT trainer. Then you have accelerate and xformer. So again, these are just to improve the inference speed of your model. So there are other libraries also. So you have VLLM. So VLLM supports all like very recent large language models, and then you are able to inference very fast. Also, people have moved towards this Grok. So I don't know, so people know about Grok. So Grok is a platform, is a website which is dependent. So which uses this LPU. So LPU are the new future. So language processing unit. So if you compare, so for example, I can just show you. So maybe it's a console.grok, and so suppose I'm just asking write a 2000 words, uh, 2000 words essay on AI, and suppose I'm using this like 70 billion model, right? So it's supposed so these majorly these four models, Mistral 8 cross 7B, Llama 3 8 billion, 70 billion, and Gamma 7 billion. Suppose I'm using this model, and I just pass this as the prompt, and you can see how quick this Grok is able to generate. So how fast the inference is. So upon like recent works have shown, this is 18 times faster than your normal chat GPT works, or like how your normal GPUs, how these like models are inferred on GPUs and all. It's because of the LPU. So how they store this. So have you like, so there's a paper, 1.58 bits paper, which recently came up, right? So they eventually, that paper led to this like development of LPUs, language processing unit. Sorry? LPU is a language processing unit. It is very similar to TPUs and all those things. So basically, they store the tensors of your embeddings, let's say. They store your embeddings certainly, then you're able to infer. So again, like these are certain libraries which are used for your faster inference. Then you have WNB. So again, like WNB is very popular for monitoring your logging and your training process. Then you have datasets and grading. So this is just for like simple user interface. So if you wanted to infer, let's say one prompt at a time, or let's say a couple of prompts at a time, so you people use Gradient for that. Then we are like importing all the necessary libraries. So once we are done, we'll be using like certain functions. So again, like you can try it on your own. And so I'll request like everyone to just create a copy of this Colab notebook and like start doing on your own. Like that will give you a better hands-on experience. So what I'll suggest is to go to your Hugging Face account. So if you go to your Hugging Face account, uh, go to your settings and your access tokens. Like just create a copy and use your access token in this notebook. So just create a copy of this Colab notebook, go to Hugging Face, copy your token, and then put that token over here. It will take like a couple of minutes and then you'll be good to go. Yeah. So meanwhile, let's say your libraries and everything is importing. So I'll just start. So let's say what are the type of data sets? So I was telling you about like there are certain data sets and you need to prepare some instructions. So how those instruction will look like. So this is a sample snapshot of this Open Assistant data set. So if you look at this row, so here you can see. So you have the certain, let's say delimiters are there. So let's say triple hash, then you have human colon, and then you have certain instruction. that you write a short introduction about relevance of the term monopsony in economics and certain, right? And later on, so then you have the conversation for assistant also. So then the assistant starts, and after a certain time, so then again the human starts, right? So and then there's you can understand in this way, there's a conversation that is flowing, and one conversation is between human and the other one is between, let's say, your assistant or your bot, right? So this is like one data set which looks like. And then you have this OIG data. So here you can also see, so here you have this human. So there's a delimiter of human. Then there's, let's say, write me an article about the Czech immigration, World War, etc., etc. And then later on you have this bot. So you have, let's say, separate, like separators are there. And then you have, let's say, a full conversation is flowing, right? So you can understand it that way. Then also a very popular data set is this one. So this alpaca GPT-4. So if you see over here, so there's this instruction, like reverse engineer this code to create a new version. And then in your input, you have this, a function of, let's say, recursion. And then in output, you are supposed to generate, let's say, here is a new version of code that calculates the factorial of number. And then the exact, let's say, this is the updated version of this recursion code. And then there's a column of text. So text basically represents your instruction, input and output, everything all together. So this is how this everything is placed. So initially you will have this instruction, that below is an instruction that describes the task, paired with an input, something, and then you have your certain like input. Let's say write a response, and then you have instruction. So let's say triple hash instruction, and then your instruction followed by your the input, and then later on the output. So this is how your overall text looks like. Right. So what we'll do is, like, we'll be using this Alpaca GPT-4 model data set, and then we'll be using it on the Llama 2, let's say Llama 2 chat version, 7 billion model. So again, let's say you're feel free to like use any other data set also, that is also perfectly fine. So what we'll do is, like, we'll import the model. So I'm using this meta like Llama 2 model on this GPT-4 data set. And so once you are done, let's say coming back to your, let's say, this thing authorization. So once you copy paste, so then your like Hugging Face will be linked, and you will be able to write your models and push it to your Hugging Face account. So once you are like once this thing is done, then maybe let's say create your Hugging Face repository. So whatever repository you wanted to create on Hugging Face under your name, let's say I can put like anything over here. Let's say instruct to something like that. So 7 billion. Right. So once you are done till this point, then maybe like we can start with the data set, like how to understand the data better. Mhm. So so this is the data set which we are looking, right? So maybe I'll just zoom in. So this is the data, like Alpaca GPT-4. So here you have like certain splits. So you might be having for train, validation, and test. And so give in this, so we only have 52,000 rows in your train. Let's say if you have a certain, like say you have a very distinct kind of validation and test data set, then you can put, when you upload your data, it will ask you. So whether you wanted to, like, how much split you want. So I think that the person might have already. Right. And another, let's say the example I was telling you. So you were having this initial prompt, then you have your instruction, your input, and then your response. So if you look in the data, so you might feel, so it is not necessary that the input will always be present. So let's say if you are, so it might also be possible. Instruction is give me 3 tips for like staying healthy. And then your output can vary, right? So there's no input you can give over here. So your input is already your instruction. And if you look, so the model is able to generate, let's say, these are the steps to keep you healthy. Or let's say, what are the 3 primary colors? Or even, so another example could be, so let's say, explain why the following fraction is equivalent to 1/4. And in your input, you are saying like 4 divided by 16. And then you have in your output, the explanation is given. So let's say the fraction 4/16 is equivalent because of these reasons. And then this text is just a concatenated version of all the 3 inputs. So like at certain places, these inputs are missing. So like I just wanted to point this thing out because it is not necessarily everywhere it is necessary. So once we are done with just like importing, so now we want training data, we only have 1000 rows. So our training, the length of our training data is only 1000. And now we will load this model. So we have earlier defined, right? Like, so we'll be using the Llama 2, but we can't load Llama 2 directly on Colab. So we'll be using the quantized version. So for quantization, so we are using over here the standard loader. So the basic version. So, and to load this thing, we'll be needing these bits and bytes. So we can't directly, so this is a very popular library, bits and bytes. So what we'll do is like we will specify, let's say load in 4-bit. So whatever the, let's say earlier encoding was FP32, full precision, then you have FP16 is your half precision, then your 8 bits, then your 4 bits also. So we'll be using everything. So let's say load in 4-bit is true. So this means that the Boolean indicating whether to load the model in 4-bit precision. And this significantly reduces the memory footprint, enabling large models to fit in our GPUs. Then you have NF4, which is, let's say, the quantization type you want. So this means normal float 4. Then you have FP, F is your full precision, and you have the certain encodings, like, or let's say quantized values you can use. Quantization types you can use. Then be using the compute type. So everything will be in float 16. So whatever the 4-bit quantized weights are there, so everything will be stored in your half precision, right? And then you have your, whether you want to use the double quantization. So let's say double quantization is something, let's say you have a 4-bit value and then you again apply the quantization. So whether you want to still like decrease it. So we won't do that, but let's say we just wanted to quantize. Let's say we are just specifying these are the parameters of the quantized values the configuration will be using. So what exactly I mean by quantization? So I'll just recap like what quantization is. So these are just like some notes. So let's say quantization. So it is nothing. It is just conversion from your linear memory format to lower memory format. So what I mean is, so let's say given this is your neural network, and in this neural network, you might be having weights. So weights are nothing. These are just the matrices. And in these matrices, so let's say every value in this matrix represents, let's say, 32 bits. And 32 bits mean like full precision. And what we will do is, let's say earlier the value is, let's say 7.2341, something like that, right? And then we want to decrease the 32 bits to, let's say, int 8, or let's say signed 8, or let's say you have the signed 128 or some unsigned 128, something like that, right? So you might want to decrease this, let's say, to bring this memory format to a lower memory format. Then you have this, so give an example. So on our GPU, so it was taking, let's say, to load this Llama 2, it took around 28 GB. But once we were using this VLLM, so the quantized version of Llama 2, so it significantly reduced to 16 GB. And also like Phi 2 model also we were able to load it under like 12 GB with inferencing and everything, with weights and everything. So, but there is a huge catch of accuracy. So if you are bringing the precision down, then you will be facing some difficulties with the accuracy. So you might be not getting the same accuracy, but people like recent works have shown this is like quite comparable. And then, so again, so what are the, how to perform this quantization? So the first technique is symmetric and then the other is asymmetric. So let's say if I talk about symmetric, so what I mean is, so let's say you have a matrix, and in this matrix you have certain values, and the range of these values, like say 0 to 1000, right? So your weight, values of your weight is between these ranges. And every let's say every value represents a 32 bit, and you're bringing everything to, let's say, unsigned 8. So unsigned 8 will have this range of 0 to 255, right? Because there's no sign involved, let's say minus or plus sign. So you want, let's say you have the scale of 0 to 1000, and then you have the scale which you want to bring this to is your 0 to 255. And given your, let's say x is your input, and let's say x is just a value in your matrix, which is, let's say, 250. So this 250 needs to be mapped to which scale? So people might argue, let's say we can use normalization. That also makes sense, which brings down to this scale, right? So let's say this is very similar. Symmetric is nothing, just like consider this thing is like very similar to normalization. So let's say you have this floating point 32. So how exactly a value is stored in this floating point 32? So you have certain bits in, let's say, like certain values are there. So let's say one bit is for your sign. Then you have, let's say, 8 bits for your exponent and 23 bits for your mantissa. And let's say 7.32. So 7 is a positive number. So here 1 will be stored at your sign, 7 is stored in your exponent, and 32 is stored in your mantissa, like 23 bits. And suppose you wanted to bring everything down to half precision. So half precision is like FP16. So FP16 will have your 1, 5, and 10. So 1 is your sign, 5 is your exponent, and then 10 is for your mantissa. Right. So let's say again coming back to your this bringing down the scale. So scale looks like this. So x max minus x min divided by x max, like q max and q min. So x is your input, the weights, the range of your weight, and q is your the scale which you want to bring to. Right. So let's say our values were 0 to 1000. So 1000 minus 0 divided by 255 minus 0. So you will get some value. So this is your scaling factor. So let's say 3.92. And what we will do is like we will, let's say whatever input, so you wanted to map 250, right? So 250 divided by this scale factor, and then you will round this thing. So once you round, so you will get, let's say, 64. So your earlier, the value which was in, let's say, range of 0 to 1000, which was earlier 250, will be mapped to 64. Like very simple maths, nothing fancy. And another kind of technique is your asymmetric. So asymmetric is also like very similar. So let's say you have weights. So it might be possible that the weights are also in negative. So what we can do? So let's say our weights varies from range of -20 to 1000. And then you are using this quantized range of, let's say, unsigned 8. So then the value of this, your range will be 0 to 255, and which basically means like -127 to 128. Right. So again, if we use the same function, so scale, then you will be getting some scalar factor, you will be getting some scale factor. And whatever values you are getting, let's say, you'll just divide and do the rounding, the same technique, right? So, but there's this issue, let's say if you have a value in negative. So then again, after this rounding up, you will get a minus 5.0. But our scale only like captures from 0 to 255. So what we can do? So this is referred to as our. So let's say what we can do. So maybe we can just sum with the same number. So if the lowest value is, let's say, minus 20. So let's say minus 20 was there, and you get your the let's say the prediction, the distribution. So let's say the scale factor of this, our quantized values is, let's say, -5. Then we will just sum with the same number. And then you will get this 0. So this means, let's say, -20 will be mapped to 0. And then the same number which we added, this will be referred as a 0 point. And if you look, so for the symmetric one, the previous technique we looked, so the 0 point was 0 in that case. Right. So we can say, let's say scale is 4 and 0 point is 5 in this case. So very simple, like nothing fancy. And then people use like quantization for like, during the pre-training also. And once the training is completed, so for the inferences also people use it. But coming back, so this was just the idea of how quantization works. So coming back to our code, so we have just defined like how we will be using everything, right? And so let's say we have, so we'll be importing the model again. But while importing, so like we are using this auto model for causal language modeling. While importing, we'll be just adding, let's say, BNB config also. So this BNB config will ensure that our values, our weights are in the quantized weights. And we have already defined like which type of quantization technique which we'll be using. So we can use like asymmetric or symmetric. Then here we are just using normal float, right? So we have just defined the quantization configuration and then the device, let's say which GPU we want to use. Then like what additional things which we wanted to do, right? So we have this prepare your model for k-bit training. So this is very necessary. So this function will ensure that let's say whatever modification or optimization you are there, like this just like tells your model that you will be using low precision weights. So you have specified this thing, and this is like very crucial for your to train the model, because we are using this quantization aware kind of training. So people refer this thing as QAT. Then you have defined this thing, all your model is imported, and whatever model you are getting, so the number of parameters remains the same, but the quantized values will be there. And then you're just saying, let's say, I just don't want to use the cache. And then you have this pre-training TP. So this is basically for like setting your pre-training tensor parallelism factor. So whatever the quantized weights you are getting, so those are, let's say, in parallel you can use on multiple GPUs. Right. So then again, like the standard tokenization, we import the model. So we have imported the model, the quantized model is ready. So what we will do is like we'll be using the tokenizer. We'll just initializing the tokenizer. So we are just importing the tokenizer, and then you're also specifying, okay, the tokenizer needs to have this end of sentence token at the last, and then this will be your paddy token, and then you're just specifying, okay, I just want a end of sentence token as well. So I just looked like how many number of tokens are there. So I was using a very less tokens. Like the vocabulary had very less tokens. So again, we'll be using this W and B. So maybe just like for the timing, just run till this cell and go to W and B and get your key. Uh, which one? This one. So if you have done this, okay, I see, I see. So maybe you can use some other model. So I have added this if you wanted to use, let's say, Flan T5 Excel. So I think that is publicly available. Llama 2, like I had this authorization, so that's why I got it. Yeah. So maybe use this Flan T5 so that like you can do. So instead of like I'll just make changes and yeah. So just make this change over here. Like instead of using Llama, you just use a Google Flan. So just run it again and then you will be good to go. Morning. And it's only on Discord. Yeah, yeah, just this quantization nodes. If it's done, so just copy your like go to WNB and copy your token. So like we are able to like log everything. So just go to this WNB and then I guess it's over here. Mm. So even if you're getting this error, so this error is just for this configuration file. So for Flanty, like I made this notebook for Llama, but if you're using the like the same configuration file, so because of this thing, auto model for causal LM, so we need to like update it. For Flanty 5, if you are using the same configuration file, then it will work. Flan or for Flan, it will give error. So I'll let you know this thing. So maybe let's say we are using Llama again. We are back to Llama, and we have loaded everything up. So we were over here, and we have loaded our model. And let's say we have pasted our WNB key as well. And so WNB key you can get it from your profile. And once you go to your profile, let's say settings, and then the API, this danger zone, and maybe you just copy your key from here. And once you paste your key over like back to your notebook, so you need to put this key over here. Fine. So just let me know if you paste this key over here. Llama is, I guess, 14, no, 12.9 GB it was taking during training, the quantized version. Mhm. I didn't put it on GPU. Matlab, like while I was training, I just kept a track of ki GPU pe kitna, like how much memory is it. So just like paste your WNB key over here. Maybe I'll fix that. So I'll just resume. Let's say you have like pasted your key over here, and so you just need to like initialize your W&B class, like which project you will be using and which type of, let's say this if this is a training or let's say inferencing, or then let's say an anonymous means like anyone can push over here. Let's say given this key, like anyone has this key, so they can like push. And if I just look like how big my model is, so if you see over here, so this is a very, let's say the quantized version. So I had this Llama 2, which is 7 billion. I have quantized it to a very small model. And if you see, so the embedding also is very small. Like the embedding is like this, just 32,000. And then like the last head was also like say 4 cross 4096 cross 32K. And once I loaded everything up, then I'll be using my quantization technique. So I'm using this LoRa over here. So let's say LoRa has certain parameters which I'll be using. So a very important factor is the alpha. So alpha is like LoRa alpha is your scaling factor for your LoRa updates. So let's say this parameter is used to scale the low rank matrices. So consider you have a matrix, and in this matrix you have certain rank. So in our, let's say, high school, we used to calculate like this is the rank for my matrix, right? So you wanted to reduce this rank to a very small number. So earlier, let's say rank was 13, and then you want, let's say, rank to be reduced to 2 or like 1, right? So this is just a hyperparameter people have tried out with, and then higher value can amplify the update, potentially leading to a faster convergence. The reason being the same. Let's say if you have a very so how fast like convergence is observed is the following. So let's say you have a higher matrix. So let's say 4 cross 4, and if you're using this alpha of, let's say, alpha will give you a matrix of 2 cross 2. So if you're reducing everything from 4 cross 4 to 2 cross 2, then your inferences will be faster. Then you have this dropout. So again, the dropout, so between the LoRa layers. So let's say dropout is just like the normal regularization we use in our neural networks. Like this prevents to hyper overfitting, and then you're by, let's say, randomly just making some of the values as 0. Right. So let's say 0.1 means like 10% are dropped out. So let's say we are just dropping out 10% of our the quantized values. Then you have this rank. So rank 16 means like whatever matrix you are getting, you will try and try to make this matrix to a 16 rank matrix. And previous works have shown, let's say this rank of 8 to 16 is quite a good number. Right. And then you have this bias, so whether you wanted to quantize the biases or not. And then you have, let's say, task type. So let's say you are using this language modeling of causal. So causal language modeling, and if you wanted to use it for your another, let's say, the normal mass language modeling, so that is also possible. Right. Then let's say which part of your transformer you wanted to use the quantization, like apply LoRa to. So then we want, let's say, QKV and your output, and then your gate and outputs. So here means like which part do we want? So let's say our output gate and up projection layers. So this is in our control, how we wanted to do it. Then very similar to a normal transformer pipeline, then you have this training arguments. So I guess like I don't need to go through all these, but like I'll just give a recap. So output directory, which you wanted to store, the number of training epochs, how much that like the number of epochs you want to train this model to. Then you have, let's say, per training, like per for training, like how many instances will be there in per batch. Similarly, you have, let's say, train eval, like per device eval batch size also. So let's say while evaluating how many number of instances should be passed. Then you have this gradient accumulation step. So this is very necessary. Let's say if given your given if you have a GPU constraint. So people use it one. So let's say after every step. So let's say, so just read it over here. So this helps simulate a larger batch size when the memory is limited by accumulating the gradients over multiple steps. So what it will do is, let's say after 2 steps, then it will compute the gradients. So if you keep it one, so every after 1 step, it will compute. But let's say given, so let's say after 10 steps have been passed, then it will compute the gradients. So this is in our control, so that we can keep everything under, let's say, 32 GB or let's say certain GPU limit. Then you have this optimizer. So we are using this Adam W8-bit. So this is a like this determine the optimization, like which optimizer which you want to use. Let's say save steps is 1,000. So let's say after every 1,000 steps, you will be getting a checkpoint. And then you have this logging. So let's say after 20 steps, you wanted to log everything. You wanted to log, let's say, what is the current loss, training loss, or validation loss, or something. Like we have like certain parameters. Then which learning rate you want. So like ideally, like so for 8 to, let's say, 2 to 8 billion models and like larger. So a very smaller learning rate has always given better results. So we were trying out, and we've observed, let's say, 2 to 2e like -8 or 9. So these actually gave us better results, and the model was able to converge better. Right. So like smaller learning rates are always, like, say, given these large, very large language models. And then you have this weight decay. So this is again, let's say, a regularization technique to prevent overfitting. And this penalizes the larger weights. And then you have this FP16. So we are not using, because anyways we are done with our this precision settings like earlier. So we are not using those. Then you have this max grade normalization. So this is just a gradient clipping value, so that you don't face this gradient exploding problem is not observed. Right. Then you have this maximum steps. So let's say this allows for an absolute number of training steps to control the training more precisely. So again, like, this is not a very important parameter. Then you have this warm up ratio. So this basically helps to stabilize the training. So let's say for like 3 steps, uh, let's say for certain threshold, the model will learn, but the gradients won't be updated. It's just like 0 shot. Like, so the model basically adjusts itself. So moving on, so you have this group by length. So this is just like you have varying lengths, right? Like, so training instances might have varying lengths. So if you're not using those, so like this helps by grouping the lengths. Like every batch should have this similar lengths. Then you have this scheduler type. So let's say how you want your learning rate to change. So you have this LR scheduler type. Then you basically report everything to WNP. So that is also there. And then you have this PEP. So from this PEP, we are using this SFTT. So SFTT is your supervised fine-tuning trainer, and you are passing your model. Then you have your data set and your PEFT configuration. So PEFT configuration, so we have defined it earlier. So initially we have this, let's say, LoRa configuration. So whatever the quantized, like which technique which we're using, so we are using LoRa. So all the configuration of LoRa is passed to our SFTT. So this will ensure. And then you have, let's say, maximum sequence length. So automatically the model adjusts. So whether you wanted to use the maximum sequence length of your model or your data. So this also is taken care by this maximum sequence length. Then you have your dataset text field. So let's say earlier we were using this, in our process data, we have a column of text. So we are passing the text in itself. Right. So that is there. And then you have this tokenizer, then your arguments and your packing. So packing is nothing. So like when set to true, packing combines multiple sequences into a single batch to optimize the memory usage. So let's say you have different sentences, different rows with different lengths. So it will pack everything up. So that's just like similar thing. So that you have your control of your storage of your GPUs and all. Right. So like you are able to process the long sequences. Then what we will just do is like we'll train this model. And if you go to your WNB, so I have specified over here. So these are, let's say, different instances I have run. So I ran it like so for like only for 60 steps. So the model was like, say, training actually. Right. So this is WNB is just to keep a track. So similar to, let's say, TensorBoard or other platform also. So like I was just training and I was just keeping an eye on training loss. So I have not specified my eval loss. So I was not able to keep a track of my eval loss. So this is how I'm just keeping everything up, and I'm just saving everything. So if you do this, so once you are done, so what you want to do is, so this is a very important step. So while we use the quantized versions, so what exactly is happening is like your main model is preserved. You're only training on these adapters. So once you are done, once you are training these adapters, you wanted to put the weights in your main model also, right? So because you wanted to infer from your main model. So what exactly will happen is like I'll just save everything to my new model, and then I will infer on my new model, right? So what I'll do is like so this again, so this is from my WNB logs. So WNB will give me a URL which I can share with my like folks, like with my friends, and like what was the loss, what was the runtime, how much GPU was used, and what was the learning rate, and it will also give you a history also. So let's say how does the epoch looks like, and then let's say how was the log, like whether the loss was like decreasing or not. So it will give you a histogram also for that. And then it will just print on the model, like how exactly the model is looking like. So you have this. So earlier, if you look like previously, so we were not having this QProj everything, right? Like so everything was, let's say, in a sequence, and over here like everything is spread out. So again, this is just a visualization. So here you can see like what exactly is going on. So let's say you are having this, let's say, key query and value. So if you look at your queue, then you have this LoRa. And in this, you have a linear 4-bit. This is attached, which was earlier not attached. So this is after the training is done. And then you have this, everything is there. Let's say LoRa A, LoRa B. So if you look in the theory, so you have this two matrices, A and B. So suppose how you define this A and B is as following. So you have a matrix of, let's say, okay, I defined it over here, I think. So this A and B looks like this. So this is like what exactly LoRa does. So instead of updating it with, it keeps a track of changes. So let's say these are your W0. And then you have like using your gradients, you get this matrix of 3 cross 3. Right. So again, and then you basically update, like say W0 plus delta W, and then you'll be getting this matrix. So what exactly this LoRa will do is like it will take these gradients. So whatever the gradients, or let's say whatever the matrix you are supposed to get, it will break down this matrix into vectors. Let's say, for example, this is a vector. We can keep it as a matrix also. So it will break down into two matrices, A and B, such that their product results into this delta. So a very simple thing, and then the values stored in these vectors or matrices in this A and B are your normal, like the quantized versions of your, like the, let's say earlier it was FP32. So these are, let's say the values over here are FP4 or 4-bit, you can say. So this A and B are your these values. So LoRa A and LoRa B. So here you can see the matrix, let's say 4 cross 96 and cross 16 cross 4096. So this 16 represents your rank. So rank we have defined earlier, right? 616. So this is there. So earlier the matrix looks like, so the base layer, if you look over at the base layer, so earlier the matrix was 4096 cross 4096. And then you are having a huge matrix. And then you have broken down this matrix to smaller matrices. And then the size is 4 cross 96 cross 16 and then 16 cross 4096. Such that if you multiply this A and B, it will result to your main matrix, M cross N. Right. So this is how you're broken down this everything, like the weight matrix or the gradients. Right. So I guess like till this point, this is clear. And then in our example, it is 1. So in this example, this is 1. So this looks like a vector, but ideally rank could be, let's say 16. So this looks like a matrix also. So this is how your MLPs, or let's say adapters, look like. So what we'll do is, let's say, okay, so another thing to measure over here is we are using lesser epochs. So in our example, we have only used it for one epoch, which is again like very less. And on one epoch, it took around, so Llama took me around like 1 hour on one epoch, right? And then we were only using 1,000 samples. So again, like so the data set was very small, and the non-hyperparameter, like we didn't do any hyperparameter tuning as well. So if you look, so the model was decreasing, but the model has not yet converged. So this was just to show like how everything is working on. And let's say, suppose if you wanted to infer, let's say what exactly is going on. So right now we have trained the model, we have kept the logs also, right? And suppose we wanted to infer. So I'm using this, I'm created this function stream. So what this function stream will do is like I'm passing a token, I'm passing a prompt, and this is my user prompt. Right, and I'm just saying ki, okay, I wanted to use this CUDA, like the inferences will be done on CUDA. Then I'll be having I'm passing a system prompt also, which I have said like initially, like below is the instruction that describes the task, and then you appropriately you need to complete the request. So this is the prompt I'm passing to the model. So, and this thing will be concatenated with the following. So you will be having separate, let's say, different, let's say, separators. So one is the instruction and the other one is your response. And then whatever the system prompt you're getting, so it will look like as following. So the input to the model will look like as below is the instruction, this thing. Then you'll be having your instruction. So this being instruction is your beginning of instruction. And then you will be having your prompt. So again, like I'm using the strip version of this prompt. And then later on, I'm just passing this as the end of my instruction. So that instruction means my response. And then the model is supposed to generate after this response. Right. And I'll be passing this prompt to my tokenizer. I'll be getting some input IDs. And then I'm using this text streamer. So what this text streamer will do is like, it is just to skip the prompt. So let's say we have seen, let's say certain times the model is generating the input again. So if you ask, let's say in 2011, what was the GDP? So it will just say in 2011, the GDP was, right? So just to skip this input and to skip the special tokens also. People use this text streamer. So it will just take the inputs from our tokenizer, and then I'm just passing, just say skip my prompt, the input prompt, and skip my special token also. So let's say end of sentence and all those tokens will be skipped. Then I'll be getting the values, and I'm passing this streamer to my model.generate. So whatever inputs I'm getting, I'm just passing this thing, and I'm taking the first initial, let's say 500 sentences. So the model was not, so once I run this, so the model was not trained enough. So the model started out giving, let's say, some gibberish, and it was some generation in German. So which translates to as following. So the prompt I passed was like, you have to propose an ethical solution to the problem of data privacy. So then the model started out giving a generations on its own. So the if you look, so the focus. So this is like how we infer also. So another example was, so I was doing this way back. So I think the architecture was Llama 2 again, and then the dataset was the full like 50K sentences. And I ran it only for 5 epochs, and the precision was FP16. And on, let's say, 2 cross V, 2 V100s, 16 GB each, it took me around 2 days just to fine tune. So this was very huge. But if you let's say play with the LoRa ranks and all other settings, so you can decrease everything. So this was the training part, and then you can just push the model again. So but while pushing, you need to take care. Let's say if you are training on your if you were training your LoRa adapters, so you need to put the adapters along with your main model. So how we can do it is following. So let's say you train your model, right? Like using your trainer, you have trained your model. So what you will do is like you will just pull the model, the main model, the base model, and I'm just doing, let's say, I'm keeping everything. So whatever my adapters were trained on, I'm just using the same model, the same configuration in my model. I've downloaded this base model. I'm using this PEFT model and the newer model which I have got earlier, the adapters. So I'm just using those models and combining, or let's say updating my base model. So I'll be getting this my main model after this concatenation, or let's say merging of both adapters and my base model. And then basically I can just push it to my Hugging Face. So but the main focus on this instruction finding is nothing. So you just need to have this instruction, the instruction kind of data set. So these instructions are something like which people are working. So this is like very similar. People say like, why don't you compare it with RLHF? So that is also comparable. Why don't you use it with drags or something like? But people are trying out, like say, given these instructions, model has given better results. And even so, this was very surprising. So let's say this instruction. So if you look like the system prompt, so again and again you are passing it to the model, but somehow the model has adapted. Okay, this prompt I'll be getting back and forth again and again iteratively. I will always see this with every input I'll be receiving. And then this instruction, these tokens also keep on coming back. So these three things also, if you have input, the input will be also be like iterating. So again, you will see input again and again. So this is something key model has adapted to. So this was very surprising, people have shown. So this was everything about instruction fine-tuning. You have this data set, and then you follow the standard fine-tuning. That's it. Like nothing fancy. It's just the data set, how well you have defined this data set. So I guess that this was it for this instruction finding. If you have any questions, so just let me know. Yes, the error was just for the access. Like I already have access to Llama 2, so I just like directly took it. But for Flan T5, so again, we were using it for our previous experiments. So I guess we hope this is okay. So this is where we were using this Flan T5 for fine-tuning purpose. Like preparation of data set is very simple, but let's say I wanted to use this Flan T5. So I have just defined my model name, and after like defining, I'm just importing over here. So if you use like this auto model for seek to seek LLM, and just don't pass this access token. And then just like a remote trust code, trust the remote code, and then that's it. You'll be able to load the Flan T5 versions. So this is like what was missing in the previous, but for Llama, it was very simple. I'll just put it on Discord. I'll just update the notebook and I'll put it back on Discord. But this was very simple, let's say. Like any other questions on this? Yeah. Fine tuning, you can evaluate. So let's say this was on instruction. So maybe you can use causal language modeling. So let's say here we were generating, let's say token by token, right? So you can use perplexity or some other metric also. Or maybe if you have some benchmarks, so let's say MNLI dataset or some other, let's say MMLU dataset, language understanding dataset. So that can also help you evaluate so how well your model is generating. Perplexity is another way. Sorry. Right. Hmm. That is anyways there. Let's say even if you have a so like if I understand the question correctly, so let's say you're using a 70 billion model and fine tuning that this model on your 100 samples data. And now you don't know whether the instructions are coming from your training data or your main model. So that we don't know. There comes the part of your interpretability. Like from which knowledge is it taking? Is it the previous existing knowledge or your fine-tune knowledge? So what you can do is like you can perform this zero shot and then check the generation and then you fine-tune and then you check the generations again. Then you can see the shift in your generations. Uh, Could be, but like from our experiments, we have seen, let's say, if you part the same prompt again and again, if you're not fine tuning, if your weights are adjusted and you're not fine tuning the model, let's say weights are adjusted for a given prompt, it might give you some, let's say, different generations. So maybe you can use some beam search kind of thing to look like which prompt is the most feasible, let's say top 5 or top 20, 25, something. So you can look over the multiple generations and then see which generation is the best. Like any other questions or? But majority of the focus is only like the effort that is required is on the data set preparation. So if like there are no other questions, so maybe we can conclude it over here. All right, yeah, thanks then.